In November 1915, Albert Einstein completed the field equations of general relativity. They were compact, elegant, and notoriously difficult to solve. Barely a month later, while serving on the Russian front during the First World War, Karl Schwarzschild found the first exact solution. The mathematics described the gravitational field outside a spherical mass. Decades later, physicists realized that hidden inside it was the defining boundary of a black hole. Einstein's equation does not give one universal shape for space-time. It tells matter and energy how to be related to curvature. To describe a particular physical situation, one must find a metric, a rule for measuring intervals of space and time that satisfies the equation under specified conditions. Schwarzschild chose the cleanest isolated case. The field is static, meaning it does not change with time. It is spherically symmetric, meaning it looks the same in every direction. Outside the central body there is vacuum. The source has no electric charge and no rotation. Real stars and black holes may rotate, but this stripped-down problem reveals the central geometry with extraordinary clarity. Schwarzschild sent Einstein his result in December 1915. His paper appeared in January 1916. The form commonly used today is written in modern coordinates and notation, not exactly in Schwarzschild's original radial coordinate. It says that the spacetime interval contains a time term multiplied by 1 minus the Schwarzschild radius divided by r, a radial term divided by that same factor, and the ordinary angular part of a sphere. The symbol r has a precise geometrical meaning. A spheric coordinate r has surface area for pi r squared. The new length scale is the Schwarzschild radius, 2 gm divided by c squared. G is Newton's gravitational constant, m is the mass producing the field, and c is the speed of light. Why must that combination appear? Far from the mass, gravity is weak and the metric must reproduce Newtonian gravity. In that limit, the time component encodes a gravitational potential approximately equal to minus gm divided by r, matching the relativistic geometry to the Newtonian limit fixes the factor of 2. This is not a guess based on escape velocity, it is a consequence of the exact solution and its weak field behavior. There is a popular shortcut. Set the Newtonian escape velocity equal to c, and the same expression, 2 gm divided by c squared, appears. That is a useful numerical coincidence and mnemonic, but it is not a derivation of a black hole horizon. Newtonian theory has no causal spacetime boundary and does not treat light correctly. The Schwarzschild radius acquires its true meaning only in general relativity. For the mass of the Sun, the Schwarzschild radius is about 3 kilometers. The Sun's actual radius is roughly 700,000 kilometers, so it is nowhere near being a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. If the same mass were compressed inside that areal radius, the exterior Schwarzschild geometry would contain an event horizon. What happens at that radius? In Schwarzschild's modern static coordinates, the time coefficient goes to 0 and the radial coefficient diverges. Early readers naturally suspected a physical singularity. But this apparent blow-up depends on the coordinates. It is rather like the failure of longitude at Earth's poles, a chart can break down where the underlying place remains regular. Other coordinate systems, such as those introduced later by Eddington, Finkelstein, Kruskal, and Sekiers, pass smoothly across the Schwarzschild radius. Curvature remains finite there. An observer falling freely through a sufficiently large horizon would cross it in a finite amount of personal time and would not encounter a material wall at the boundary. The genuine classical singularity of the ideal Schwarzschild black hole lies at r equals 0, where curvature quantities diverge. General relativity itself is expected to become incomplete in that regime, because quantum effects should matter. It is therefore important not to imagine the central singularity as an ordinary tiny object whose detailed physics is already understood. The event horizon is instead a causal boundary. Inside it, every future-directed path of light or matter leads toward smaller art. Escaping would not merely require a very powerful rocket. It would require traveling outside the local light cone, which relativity forbids. Light still moves locally at c, the geometry determines that all allowed future directions point further inward. The same geometry also organizes motion outside the horizon. At 1.5 Schwarzschild radii lies the photon sphere, where light can follow circular paths in the ideal geometry, although those paths are unstable. At 3 Schwarzschild radii lies the innermost stable circular orbit for massive test particles around a non-rotating black hole. Matter in a thin accretion disk can radiate intensely as it approaches this region. These radii are not extra surfaces built into the black hole. They are features of the possible trajectories in curved spacetime. The glowing rings seen in visualizations therefore should not be confused with the event horizon itself. To a distant observer using Schwarzschild time, a falling object appears to slow and fade as its light becomes increasingly redshifted. The infalling observer's own clock tells a different but compatible story: the horizon is crossed in finite proper time. These descriptions use different notions of time. Confusing them produces the false claim that nothing ever crosses a horizon. Schwarzschild did not announce the modern black hole in 1916. His result was an exact solution for the exterior field of a spherical mass, and its global interpretation developed gradually. A solution describing an eternal black hole is also not by itself a theory of how one forms. Later work on gravitational collapse showed how matter could create such a region dynamically. The solution nevertheless transformed Einstein's general equations into testable geometry. It predicts gravitational time dilation, the paths of planets and light, and the characteristic scale at which a spherical mass becomes hidden behind a horizon. Rotating astrophysical black holes require the later Kerr solution, but Schwarzschild remains the essential starting point. There is a useful philosophical distinction here. An equation's formal structure and its physical interpretation are related, but they are not identical. The factor that looked singular in one coordinate chart was not itself a destructive physical thing. Understanding required asking which features belong to the chosen representation and which belong to the spacetime being represented. So Schwarzschild's achievement can be stated precisely. He found the first exact, static, spherically symmetric vacuum solution to Einstein's field equations. Its geometry contains the length 2gm divided by c squared. When a mass lies within that radius, the radius marks an event horizon, not a surface of matter, but the boundary beyond which no future-directed signal can reach the outside universe. One exact solution, written during a war, revealed that Einstein's new geometry permitted an object unlike anything in Newtonian physics. The mathematics came first. The full physical meaning took decades to uncover. Today the Schwarzschild radius remains the cleanest doorway into understanding what a black hole really is.